Welcome back to the deep dive. Today we're tackling something a little different. Not a new piece of technology, not a business trend, but the invisible engine that really runs science, medicine, and, well, increasingly all of artificial intelligence.
And it's an engine that, honestly, is a bit of a mess.
It's a huge mess. It's the thing that decides whether a new drug actually saves lives or if we're just, fooling ourselves.
Or if a new economic policy is going to help a country or, well, bankrupt it, it's all about cause and effect.
Exactly. We're talking about the question of why. We're talking about causal inference.
That elusive why, it's so simple to ask and so difficult to answer.
And look, we all know the slogan. You hear it everywhere.
Sure.
Correlation does not equal causation. It's like the first thing you learn in any stats class. It's the bumper sticker of the intellectual world.
Right. You see ice cream sales go up in the summer, and you see shark attacks go up in the summer.
Then the rookie mistake is to say, oh my God, the ice cream is causing the shark attacks. We have to ban ice cream to save the swimmers.
And everyone else just rolls their eyes and goes, no, it's the summer. The warm weather is the common cause, the confounder that makes people swim more and eat more ice cream.
Right. We feel smart because we spotted it. But here's the real problem, and this is what we're really digging into today. If correlation isn't causation, okay, fine, then what is? What do we do instead?
That is the multi-billion-dollar question. And it turns out that for the better part of the last 40 years, there has been a kind of intellectual civil war raging in the scientific community over how to answer it.
A genuine war between two absolute titans of the field. In one corner, you've got the statistician, Donald Rubin, a giant in his field.
And in the other corner, you have the computer scientist and AI pioneer, Judea Pearl, another giant.
And this isn't just some, dry academic debate. These two men and their frameworks, Rubin's potential outcomes and Pearl's structural causal models, they see the very concept of why in fundamentally different ways.
They really do. When Rubin looks at a problem, he sees a giant spreadsheet, but with a whole bunch of crucial data just missing. Blank cells everywhere.
Okay, a missing data problem. And Pearl.
Pearl looks at the same problem and sees a flowchart. He sees a wiring diagram of reality, a map of causes and effects. It's all about the structure, the logic.
And today, we're going to try and navigate that battlefield. We're going to start by walking through what Rubin called the fundamental problem of causal inference, which is, frankly, a little bit mind-bending when you first encounter it.
It really is. Then we're going to put on our lab coats for a thought experiment about a perfect doctor. It's a story that proves pretty definitively why just having more data, big data, can often just be a big lie.
And that's going to lead us right into the danger zone. We're talking about something called M-bias and the concept of a collider. This is where the two frameworks really properly clash. It's a place where doing what feels safe, what feels intuitive, controlling for more variables, can actually introduce bias and completely break your study.
It's so counterintuitive, and our goal here at the end of all this is to sort of synthesize these two rival views into a toolkit that you can actually use, because it turns out they aren't just rivals, they actually complement each other in powerful ways.
So if you're ready to really question what you think you know about evidence, data, and truth, let's dive in.
Let's do it.
Okay, so let's start with the statistician. Let's start with Donald Rubin. When he looks at a simple causal question like, does taking this aspirin cure my headache?
Yeah.
What is he actually seeing? What's the machinery in his head?
So Rubin and the whole framework that really he championed, which is often called the Rubin causal model or the Neyman Rubin model, it's all rooted in this incredibly powerful idea of potential outcomes.
Potential outcome.
It sounds a bit technical, but the core idea is actually deeply philosophical. It says that for any single person, or any unit, as he would say, there are multiple potential futures that exist at the same time, just waiting to happen.
So it's kind of like a multiverse theory for statistics?
That's a great way to think about it, yes. A personal multiverse. Let's use your headache as the example. You are unit. In Rubin's world, there is a specific future, a specific reality, where you take the aspirin. Let's call your pain level in that future Y dollars.
Okay, so Y dollars is my outcome if I get the treatment. I take the pill, and an hour later my headache is, say, a 0 on a scale of 10.
Exactly. That number exists. But at the very same moment, another number also exists. We'll call it Y dollars. And that's your pain level an hour from now if you do not take the aspirin.
Future B, where I just, suffer through it and my pain stays at an 8 out of 10.
Right. And in a perfect godlike world, the definition of a causal effect is just simple subtraction. The individual causal effect of that aspirin for you is just your outcome in future A minus your outcome in future B. It's 1 all or -1.
So 0 minus 8. The effect is negative.